In this video, we continue our discussion of the definition of the derivative. And just to refresh your memory, remember the definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This is the derivative. This is f prime of x. It's also dy over dx. These are just different notations for the derivative. The derivative is the slope of the tangent line or the instantaneous rate of change. All right, so in the last video, we had a lot of fun expanding these binomials, and we can continue to do that. That is one way to solve this. So if you give me just a few minutes, I've already got it expanded. I just want to write it out and show you what this whole thing would be, because you know you've got to raise x plus h to the fourth, so that means 4 of those guys, and then distribute a 3, and then distribute the 2 here, and then we're going to subtract these guys. And so give me just a minute and I'll write it out for you. This is going to be 3x to the fourth plus 12x cubed h plus 18 x squared h squared plus 12h x h cubed plus h to the fourth 2x plus 2h minus 3x to the fourth minus 2x. And this is all divisible by h. Okay, and so our next step was to see if we could cancel any common terms. I got like that guy and that guy. I think we have a positive 2x and a minus 2x, so that helps a little bit. And then our next step was then to write, or to factor out an h in the numerator so that we can cancel it with the guy in the denominator, and then we can evaluate the limit. Because we can't sub in a 0 right now because of that h in the denominator. Okay, I'm thinking I got everything there. There's the h. I'm going to cancel those h's. And then if I were to substitute in 0 for h, this term cancels, this term cancels, this term cancels. So my derivative, my instantaneous rate of change expression is going to be this guy. Now, at the end of our notes last time, we talked about the power rule, and that was a much easier way rather than this whole expansion, canceling, factoring. There is a much easier way. And so using the power rule, we can save a lot of time. But in this format, looking at this is our definition of our derivative. We need to be able to recognize what the function is. And if we can find what the function is, we can easily use that power rule and get our derivative. So let me write that power rule again. I'm sorry, the definition of the derivative again, which is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So what we've got to figure out is, well, what is the function? In the first part of this, of the quotient, we're evaluating the function at x plus h. You see how we've got that here? So this is the function evaluated at x plus h. And then we have this piece here, and then we have minus f of x. Now we can't always rely on this minus f of x, so don't look at it. Because sometimes, in this case, it's an expression, and that's fine, but sometimes you just have a constant, and so that's not going to help you. So if you can just look at this part of the definition of the derivative, it might be easier later in the long run. Okay, so what we've got to recognize is, well, what is the function? Well, f of x is equal to, remember, we're plugging in the x plus h, so it'd be 3x to the fourth plus, and again, plugging in the x plus h, 2x. Now, if we apply the power rule, in the power rule, we take the exponent, we bring it in front, so this is going to be 4 times 3, and then we subtract 1 from the exponent. 4 minus 1 is 3. And again, you don't have to show all these steps, but I'm going to work through at least this first one. Okay, so our exponent on this term is a 1, so we bring that in front. And then we subtract 1. Well, 1 minus 1 is 0. So I could leave it like that. And now let's clean this up. 4 times 3 is 12. 1 times 2 is 2. And next to the 0 is 1. So look what we did, guys. We just found the derivative. Much easier than doing all this. And honestly, I saved y'all a ton of time by expanding this all out and having it here. This would take you lots of steps. Okay, let's try that again. Here's our function. Again, I want you to just ignore this part on the side. It won't always be there. I want you just to kind of see if you can figure out, well, what is the function? So let's see, we've got the x plus h plugged in here, and we've got the x plus h plugged in here. And so I know my function is going to look like this, 2x cubed minus 5x squared. If you want to expand it out and do the algebra, that's fine. This way is going to save you lots of time. So using the power rule, exponent times the coefficient, that gives me 6, subtract 1 from the exponent. Exponent times the coefficient, that's going to give me negative 10. Subtract 1, I'll just leave it as 10. This is the equation for the slope of a tangent line. Okay, now we've had x plus h. This time we have x plus delta x. So again, this is just the delta x is equal to h. That's just the change along the x-axis. All right, so let's see if we can recognize what that slope. And look, this one doesn't help us at all. So we can just scratch that out. Let's just look at the part where our x plus delta x is. This is going to identify our function as 7x squared plus 2x. Find the slope, find the derivative using the power rule. Exponent times coefficient, subtract. Exponent times coefficient, subtract. Here is the equation for the slope. All right, in this one, now we have it changed up even more. And see, here we go. Here's that constant. That's going to tell you nothing. So look at this part. Let's see if we can evaluate. And instead of x plus h this time, we have 6 plus h. So we're not only going to find the function and the derivative, we're going to evaluate it at an x value of 6. So we've got something that looks like the definition of the derivative. Let's find our function. Okay, we've got the 6 plus h cubed minus 2 times 6 plus h, so that's going to be where the x is. Let's find the derivative using our power rule. And then let's find the slope at an x value of 6. So 6 squared is 36 times 3 is a big number. 108 minus 2 is 106. So the slope of a tangent line at an x value of 6 of this function is 106. So where did this 204, like that's not just some random number. Well, that's what f of 6 is. Remember, this is f of x plus h minus f of x. This is just f of 6. And let's just make sure. So if I plug in 6 cubed minus 2 times 6, 6 cubed is 216 minus 12 is 204. All right, another one looking a little strange, and I got another constant there. So let's just, this time x plus h, this time I have 3 plus h. So I'm going to look at the slope at an x value of 3. So let's see, what is my function? I've got the 3 plus h in here, so that's going to be 2x to the 4th, 5x cubed. The derivative using the power rule, 8x cubed minus 15x squared. The derivative at 3, 8 times 3 cubed minus 15 times 3 squared. 27 times 8, 216. 9 times 15 is 135, and the slope at an x value of 3 of this function is 81. Okay, let's continue on. So what is the equation of the line tangent to the function here at an x of 1? So in order to find the equation of a tangent line, we need two things. We need slope and a point. So let's find them. Let's go ahead and evaluate, well, what is f of 1? 1 cubed minus 4 times 1 squared plus 3. 1 minus 4 plus 3 and 0. So I have the point 1, 0 on this curve. I guess I could have looked right there on the graph, but I worked it out just to make sure. And let's find the slope at 1. So let's first find x prime. I'm sorry, f prime of x. And so if I use the power rule, 3x squared minus 8x, the slope of a constant, remember that's 0. And so f prime at 1, 3 times 1 squared minus 8 times 1, 3 minus 8, and that gives me -5. So the slope at 1 is -5. So now if I want to write my equation in point slope, y minus 0 is equal to m x minus 1. I can leave it like this, or I can risk losing a point by simplifying. That's up to you. Okay, so let's use the tangent line at 1/2, 0.5, to approximate f of 0.51. Okay, so let's see. I'm going to try to draw in at 0.5. So 0.5 is like right in here. So my tangent line is going to intersect my graph somewhere like this. Remember, it only touches once. Do you see how my tangent line is above the curve? So it says use the tangent line equation, and I wish, can I zoom in? Oh, I can't zoom in. Oh, I can zoom in. There we go. Okay, I'm learning. Okay, so 0.51 is just somewhere right in here to the right. Let's see if I can come up with a better color. I'll just use black. Let's see if that works. So 0.51 is right here. Okay, so what do we think about that approximation? Is it an overestimate or an underestimate of this curve? Well, since that tangent line is above the function, we can say that it is an over approximation. Okay, again, the tangent line at 0.5 is right here. Right here. And so it is above the graph. If we're going to use that to approximate the value of the function, it's a little bit above, and I had to really zoom in to see that difference there, that little tiny bit of white right in there. This is going to be an over approximation. It's a good approximation, but it's just going to be a little bit above it. All right, and so let's use the tangent line at an x value of 3. And then approximate f of 3.01. Is the approximation an over or under? Okay, wow, look, I can really move this graph. So at an x value of 3, 1, 2, 3, here's 3 right here, I would intersect this graph like right here, right? So my tangent line, trying to only touch it once, but it's hard to draw. All right, so there's 3. That's where it intersects at 3. But at 3.01, which is just somewhere right in here, we can see that it's going to be right. You can see just a little tiny bit of white space in between. So if I use that tangent line to approximate 3.01, it is below the graph. So it would be an under approximation, and now I can't seem to figure out how to get my graph back in. There we go. So in conclusion, what I can say that, and we really haven't talked about this much, but where the function at, what was the first x value? 0.5. At 0.5, our graph was doing this. And so our tangent line was above it. I don't remember how I drew it, but roughly that's what it looks like. And then at 3, our graph was doing this, so our tangent line was below it. Just put some arrows on those. So when we are using the tangent line to approximate, if the function is concave down, then the linear approximation is an overestimate because the tangent line was above the graph. And if the function is concave up, then the linear function is an underestimate because the tangent line is below. And we'll talk about this concave up and concave down in a later discussion.